Hello, my name is Leandra Gonzalez, and today I'm going to talk about a little bit about quantum cryptography. So the content of this talk is going to be about why the interest in quantum cryptography, some concepts of quantum computing, quantum cryptography by itself. We're going to talk about two specific quantum key distribution systems and a little bit of a conclusion. The interest is the motivation of this is because I studied physics, and my main area of interest was quantum physics. And now that I am in this class of cryptography, I found that it's really interesting the mixture of both of them. Also, I was looking into something that is the Shor's algorithm. Shor's algorithm is a quantum algorithm that is able to solve the problem that actually is the backbone of the RSA encryption algorithm, or a lot of encryption systems. That is really complicated to find the numbers, the prime numbers that multiply gives me the number that I use to do all the encryption scheme. So nowadays in classical computer, we can know that the biggest number created by now is 240 digits. It's going to take us 900 years of classical computation to be able to break the code and find the two numbers, that the two prime numbers that multiply gives me the number that I have. In the Shor's algorithm is actually does this really fast thanks to quantum computing, and that's why we're going to talk about it. We're going to start with theoretical quantum mechanics, and there are certain principles. First is the superposition principle. This principle says that everything is a probabilistic state. What does that mean? That everything is in every single state at the same time until an observer goes and sees the experiment, and that is when the experiment decays and it becomes deterministic. The main example of this is the Schrödinger cat paradox. That is, that there is a cat in a box, and if you are not seeing the cat is dead and alive at the same time. But if you go and see the cat is dead or alive. That is the main meaning of superposition principle. Now we're going to talk about the Heisenberg uncertainty principle. It says that in a particle, if I know where the particle is, I don't know at what time that particle is there. And if I know the time that the particle is, I don't know where the particle is. So the exclusion between both of them is really interesting and useful. And finally, entanglement. Entanglement says that if I have two different particles that they are separated, but they are entangled each one to the other, they are in probabilistic states. But when I observe one particle, the other is going to decay too, because they are entangled. So what happens to one happens to the other, and they are exclusive, which means if one decays to one, the other is going to decay to zero. That's why in the graph we will see when Alice looks at the sock that before was pink and blue, it becomes pink, but in that moment Bob is not even looking at the sock, but the sock becomes blue, and the other way around too. Now I'm going to talk also about classical bits and qubits. Classical bits are the bits that we use normally, and here we can see the Dirac notation and the vector notation, and the qubits, in this case, we are notating them as a superposition. So alpha means that is the probability of have the bit in 0, and beta is the probability of have the bit in 1. And this is one of the most important constraints, and is the probability of having the 0 squared plus the probability of having b 1 squared is always 1. And that is when we get this, that is the Bloch sphere. That it is how we represent qubits. We don't represent qubits anymore like a point, like a up and down. We represent it as a vector. And as we can see here, it can also have like a complex numbers. Now we're going to talk a little bit about two gates, that they are the strength of quantum computation. They are C0 and Hadamard gates. C0 is called control node. Why is called control node? This gate is really similar to what we, in classical computing, we call it NAND gates. Because based on this C0, I can create a lot of gates that are actually used in quantum computing. So the important part is I have these bits This is called the control bit, and this is not the control bit. So if the control bit is 1, the second bit is going to change. That's why we see in this part, the bits are the same. But in this part, the 0 on B becomes 1 and the 1 becomes 0. And this is the other gate that is really important too, that is the Hadamard gate. In the Hadamard gate, what it happens is Hadamard is like the XOR. What does that mean? Like a Hadamard is the inverse of itself, in the same way that XOR is the inverse of itself. And also the other thing that is really important to take into account is like if I have a qubit that is in one state, is a single qubit, and I put it through my Hadamard gate, is going to become a superposition of states. This is really important because it allows me to pass from my classical observations to my quantum computations and back. Because if I do it back and forth, it will work because Hadamard is the inverse of itself. Now we're going to start talking about quantum cryptography. We're going to start talking about the Schur algorithms. It's divided in two parts. That is the classical part and the quantum part. So the classical part, we're going to do a bunch of math. And the first one is I'm going to make a guess that is going to call G. And again, I need to do the GCD between G and N is equals to 1. Remember, what we're trying here is to factorize N. There is a mathematical property that I say if I take a number and I multiply by itself several times, eventually that number can be written in this way. In our case, is G multiplied several times, P times, is going to be a number multiplied by N plus 1. And this is something important because we're going to use the Euclid's algorithms to apply there. If I rearrange here and I factorize, I get this. And as you can see, I have a factor and I have another factor. So I found factors. And I say, if this can be factorizable and this can be factorizable, I can find a shared common factor between this part of my equation and this part of my equation. And if I find a common factor in this moment, I can calculate the GCD and I have a factor for N. That means it solves the problem. The only caveat of this is that I don't know who is P. How many times do I need to multiply G by itself? And if you do it in a classical computer, it's going to take a lot of time. So this is the part that we take this and we use a quantum computation. What we do is we take an input X, and when you put an input in a quantum computing, that is a superposition of states. That's why it appears all the dots. And after that, what I do, I calculate G to the power of that state, that this is this part. After I do that, I calculate the residue because this is based on my previous slide. So I can isolate and find the residue. So after I do this, I put it through my quantum computer again, and I find the residues associated to the states, to every single state. Here, I do a little bit of a classical math that it says I find that this is, when I calculate G to the P plus X, I find this is periodical. What does that mean? That if I multiply G to the P by G several times, I'm going to find that it's always going to be in the way of something multiplied by N plus a residue, when the residue is always the same. By this principle, what we can see is that when I calculate the residue, the majority of the residues are going to collapse to the most probable state. This is one of the most important parts where quantum computing enters into play. When we calculate things in quantum mechanics, everything collapses eventually to the state that has the biggest probability of happening. In our exercise in this moment, the one that it has the major probability is R3. That's why all of these, they collapse to R3 and the others disappear. And after that, because I know that all of this is periodical, I apply the Fourier transformation, the quantum Fourier transformation, that is specifically a function that allows me to find the periodicity of a function, any function. in this case, a quantum function. So if I put these states through my quantum Fourier transformation, I'm going to find my periodicity, my frequency, that is 1 over p. And if I find 1 over p, I'm going to find p. And if I find p, as I talked previously, I'm going to find my factor of my prime number. So now, after a short algorithm, I'm going to talk about this quantum key distribution protocol. And to be able to talk about it, the first thing that I need to talk is about polarization. When we are talking about qubits and all of these, we are talking about waves. So when you have a wave, you can polarize in two ways. You can polarize it in a rectangular way, or you can polarize it in a diagonal way. So this is what is happening here. We have two bases to be able to polarize our waves. I have a rectilinear polarization, which means if I polarize 0, it's going to become a horizontal line, and if I polarize 1, it's going to become a vertical line. But if I do it in the diagonal base, the 0 is going to become a positive diagonal, and the 1 is going to become a negative diagonal. As we can see here, they have angles associated. And this is the quantum key distribution protocol. So what happens is Alice, she creates some bits, classical bits. And after that, she chooses a base. For every single one of her bits, she chooses a base. So for example, in this case, for 1, she chooses the diagonal base, and that's why it gives us that diagonal. After that, she sends the result, this sends to Bob. And what does Bob is that he chooses also bases. He can choose anything that he wants. And in the moment that when the diagonals cross to that base, is going to give us our classical bit. So if you can see here, this is like the encoding, and this is the decoding. And all of this is random. They don't talk about it at all for now. So when all of this happens, they do all of these calculations, and after that they check, they say, oh, this is my base. And after that, Alice says also, oh, this is my base. And based on that, they can check and they start eliminating the ones that they didn't use. For example, in this case, they say, oh, Alice used a rectangular polarization, but Bob used a diagonal polarization, which means this bit is going to be not useful. And that's why we can see here that is eliminated. And they do that with all of them. From there, they get a sub key that is called Siphon key. And that key is the one that they use from there on to keep sending the bits. This is really important because when we are talking about quantum, the eavesdrop, even if Eve wants to listen to the conversation or the bits, in the moment that she is going to be in the conversation, she's going to make the states change. Because remember, in the moment that I see a particle, in the moment that I interact with the experiment, I'm making the superposition to stop existing and decay to one state. So they can see, for example, in this case, if it was right, but if listened to it, probably there is a probability that this wasn't 1 but a 0. And in that moment, they can realize that somebody's listening to the conversation. And that's why this protocol is really, really secure in the case of man in the middle and eavesdropping. Now we're going to talk about the other protocol, that is Arthur-Ecker quantum distribution protocol. I didn't mention this before, but usually the protocols are named the initial of the order and the year that they did. So in this case, what we're going to use is the entanglement principle. And what we're going to do is, oh, and I forgot to say that for the other one, we use is the Heisenberg principle, the uncertainty principle, to be able to build all of that. In this case, we are using the entanglement principle. And the entanglement principle can be seen here. Here I can see that my bits, my superposition of states is or zeros or 1. But this is my state function. So what is going to happen? I'm going to have a third party that is a source. And that party is going to create entangled photons. So those entangled photons are going to be related by this. But because they're entangled, in the moment that Alice and Bob, one of them, they look at the photon, the other one is going to have the other version. So for example, if Alice look at this, if she's a 0, if she sees a 0, that means that Bob is going to see a 1, because again, it's entanglement. They are entangled photons. The other thing that is important to notice is that they only can polarize in certain angles. So Alice only can polarize in these 3 angles, and Bob can only polarize in these 3 angles. And the basics is really similar to BB84. So, but the only part that it changed is how the source is created. In our previous example, was Alice the one who created all the photons, and like she shows all of that. In this case, is a third party, and that actually is one of them. This is probably is going to be the one that is going to be more used in the future, because you can just have somebody to create your entangled photons instead of you having to create your photons to be able to create a key. Besides this, I mean, because based on this, I found that quantum cryptography has a lot of challenges. They can be divided in 4 categories, that is performance and cost, because the cost goes up if I want to get a better performance. Security attacks and challenges, as in the same way that we have classical security concerns, in the same way we're going to have it in quantum cryptography, but they are going to be a little bit different because these are based on the physics. Hardware challenges, and we can see right now, I think right now this only we have a qubit of 15 qubits between each other. So there are so many computations that we cannot make, and everything is theoretical. So we need to wait a little bit until time pass and we are able to kind of do any of the computations. I mean, it's improving, but it's still we have a long way to do it. And also the other thing that we need to take into account are the design challenges. The problem with this is like everything that you measure, everything interaction creates noise. And in the moment that you have noise, you are going to have interference, and it's going to change the state because it's going to make it decay. That is a problem, because that means that everything needs to be isolated. So it's complicated to make the design, the hardware, and everything to make it kind of work. The final takeaways from this is quantum cryptography is a huge field that there is still too much to explore, because this is based on physical quantum mechanics kind of methods that are also, again, super huge. But at the same time, there is a problem, because there is going to be a really difficult time creating and modifying quantum key distributions, because you need to be versed on quantum mechanics, quantum physics, to be able to create all of that, because they are based on those methods. The other that I talked before is like a quantum capacity is still not there. And actually, we can see, because of all of these implications, for example, Shor's algorithm, we can know that post-quantum, and we can see all these implications, like people is already preparing for post-quantum cryptography. That is not based on physical of quantum mechanics phenomena, but it's based on math. So it's more feasible to do and like to work on it. The other thing that is like this is a personal opinion about the matter, and is I think cryptography is a huge field and is interdisciplinary, and I think it's a really nice thing to see that there is collaboration between computer scientists, mathematicians, physicists, and many other people. And also for me, it was really exciting to find that the quantum phenomenon is really abstract and you cannot see it. Like literally, you're going to say you have to make all these thought experiments. But it's really nice to see that at least nowadays there is something more real and more feasible, and like you can understand better. And also, I think that it's really exciting to know that quantum mechanics can be grounded in something so close to us that are security in our communications. So I think that's all. Thank you very much, and I hope you like it.